Okay, up to this point we've been talking about functions and limits, and basically what we talked about with the limit is what's the output value when the input is close to but not particularly at a particular point. We would say what is the f of x value or the function value, and that's been a limit. And so now what we're going to do is we're going to move a little bit further and we're going to say, well, how does changing the input affect the output? And so we can use the definition of the derivative that's here to calculate precise information about how we wiggle the input affects the output. So the first thing we're going to do is just establish that. You can see that the derivative is defined as the limit of f of x plus h minus f of x divided by h as h approaches 0, provided the limit exists. And we've been calculating this before because we came to that crucial point in calculus where the limit was used to define the slope of the tangent line. And in that case, it's also used to define differentiation. So we're going to give you a few minutes to write this definition down. And this is also an alternate definition. So f prime of a in this particular case would be the limit of f of x minus f of a over x minus a as x approaches a. And the only difference is this one's more familiar to the formula we used to define slope the very first time we introduced this, where we had the difference in output up here and the difference in input or the change in the input, and this is where a is a nearby value of x. Okay, so sometimes this will just be the alternate definition of that. And derivatives, for the most part, they're important to us because they're going to be able to provide approximations for us and also explain trends in a function. Also notation f prime, that's how that's read, f prime, and also f prime of x means that f is differentiable at x. So that's just some notation to take note of. So differentiation is the process of finding the derivative of a function, and we'll practice with an example next. So let's do an example. So our first function is going to be 3x squared minus 12x plus 8. We're going to be asked to do three things with it. We're going to use the definition to find the derivative. Then we're going to evaluate the derivative at particular values of x. And find the domain of f prime of x. So first thing we're going to do is we're going to pause it and use the definition to find the derivative. Okay, so we have our definition, and the first thing we want to do is when we evaluate f of x plus h, if you see my scratch mark off to the side, that'll help distinguish the difference, and then I'm going to subtract f of x in the numerator. Okay, so that's what that should look like. Your next step, I want you to just algebraically simplify everything in the numerator. Okay, just be careful with your simplification, and also don't forget to distribute this negative to all the terms. Let's look and see what's cancels. So we have a 3x squared will cancel. What else? The 12x terms, and also that. So what do we have left? We'll have 6hx plus 3h squared minus 12h over h. And now what can we do? We can factor out an h or divide an h out of each term. So this has an h, this has an h, this has an h. So that's just going to simplify to, well, we get 6x plus 3. There'll be an h left here, minus 12. So let's evaluate that limit. All the simplification's done. Let's evaluate the limit as h approaches 0. So if we put a 0 in here, what are we left with? F prime of x. So our derivative is going to be 6x minus 12. And if you notice, the derivative is a function as well, so we can evaluate that. So part A, this is our derivative. And for part B, it wants us to we'll go to the next page and evaluate the derivative at 4, evaluate it at -2, and evaluate it at A. So let's do part B on the next page. Okay, so we recall that What did we get for our derivative? F prime of x. We got 6x minus 12. 6x minus 12. So when we evaluate f prime of 4, that's just going to be evaluating f prime of 4 is going to be 6 times 4 minus 12 gives us 12. So this one equals 12. All right. What about evaluate that at -2, and I want you to evaluate that at f prime of a. Go ahead and do those two calculations, and then you can check your answer. Okay, good. So check your answer there. Once we have the derivative, we can evaluate it at particular points. So we make those substitutions, and there's that. Part C asks us to find the domain of f prime of x. In part C, since our derivative is just a linear function here, we're just going to say the domain is all real numbers, or if I was using interval notation, I would just say negative infinity to positive infinity. Okay, in this next example, we're basically going to use the results from example 1, since we've calculated the derivative and we knew the domain, to now calculate slope of the tangent line at a particular point P, and then also find the point at which the tangent line is horizontal. So we're going to do two different things. First of all, for part A, the slope of the tangent line, what is that? That's what we calculated, right? The derivative. So let's look back at that. So this is what we've calculated right here. This is the slope of the tangent line, which would be 6x minus 12. So that's also the derivative. So we come here, and for point A, we're going to use that previous information. We've already calculated. So point A, we're going to have slope is going to be given as 6x minus 12, which that's also our first derivative. Okay, but we want to evaluate it at the 0.31. So what do I do now? Plug in the what? X value of 3. So we're going to substitute that in. So I'll have 6 because I have this point P. So that can be represented as f prime of 3 is equal to 6 if I wanted to change just the notation of this to match what we're doing today. Okay, f prime of x was 6x minus 12. We evaluate that at 3, so f prime of 3 is 6. Okay, so this is going to be my slope is 6. Now, the slope of the tangent line, that's all that it asked me for here. Slope of the tangent line at that particular point. All right, now for part B, the point at which the tangent is horizontal. What do you know about when a tangent line is horizontal? So like for example, if I just had some function like that and I'm looking for when, let me change color, my tangent line, pretend that's a straight line, is horizontal. What does that, what's the slope of that particular tangent line? 0. So what can I do here? Take your slope of your tangent line, which is defined by what? What did you tell me it was for our particular problem? 6x minus 12, right? And you said set it equal to 0. Good. So let's calculate this and see what value of x satisfies that. So the algebra is really basic here. 6x. So when x is equal to 2. Okay? But we need a point, an ordered pair point. So what am I missing? I have the x value of it, so I know the point 2. How do I find my y value? Plug it into your original function. Good. So my original function is just 3x squared minus 12x plus 8. Let's plug that back into our original function, and we're going to evaluate it when x is 2. And then calculate that. That's 2 squared is 4. So 12 minus 24 plus 8. So at the point 2, negative 4. That's point B.